Welcome to the second lecture in topic 5. This is all about chemical formulas and the math of chemical formulas. So it's mostly empirical and molecular formulas and how to use elemental analysis or combustion analysis to determine empirical and molecular formulas and in other ways. So this is not stoichiometry of reactions. This is simply about one substance at this point. So we're going to use some of the things that you learned in the previous video, like using the percent composition or the part over whole of the molar masses as a conversion factor, and we'll use a few other things. Some of this will be review for you. The part of how to calculate an empirical formula is pretty much review, but the part about finding the grams of your elements will be new this time. So definitely make sure that you have your foundation set from your learning targets here in your notebook. Really have a good foundation of what the book says about all of this, and then we're going to come back in and add some information after you're done with that. So if you haven't done it yet, make sure that you stop the video here and do your learning targets. Otherwise, we're ready to go. Make sure that you're going to add to them as we go. I'm going to give you several examples. All right, so the first thing that I want to talk about in this video is the definitions of empirical and molecular formula. Empirical formula has to be the simplest whole number ratio of the elements in a compound. And for ionic compounds, pretty much we always use an empirical formula, but for compounds that are made of two or more nonmetals, we often will not. They don't exist as an empirical formula. So you have to just kind of keep in mind that if you're talking about an empirical formula, it may or may not exist that way as a compound, but it will always be represented as the simplest whole number ratio. And of course, that's the ratio of subscripts. Okay, so this would be the subscripts are in the simplest whole number ratio. Molecular formulas are how the compound really exists. It could equal the empirical formula, or it could be a multiple of the empirical formula. So we always think of it as a multiple of the empirical formula, and the multiple might be times 1. In other words, they may be the same, but it's always a multiple. So because of that, they will have the same percent by mass. So it doesn't matter, percent by mass doesn't tell you anything about whether or not you have an empirical or molecular formula. You have to know the molecular mass to know whether you're talking about the empirical or molecular formula. So notice that this is an example from your book that we have all of these different compounds that all have the same empirical formula. Every single one of these would reduce to CH2O. I can divide this by 3 and get CH2O. I can divide this by 4 and get CH2O, etc. Okay, so all of these are very, very different. They have different functions, they have different properties, and the only thing that's different between them would be the mass. So remember that this multiple is 6 of CH2O, which is the empirical formula for all of these, okay? And the multiple of glucose is 6, so notice that the mass is also, to get from 30 to 180, times 6. Or in this case, acetic acid, the multiple is 2, so the mass is also a multiple of 2. And the mass is going to be how you identify what your molecular formula is. You'll have to decide, what do I need to multiply by, multiply my empirical formula by to find the molecular formula. So let's remind you how to do this. This would be review from first year. Okay, so you, to calculate the empirical formula, are going to determine the mass of each component element. You might have the percents first, in which case percents get changed to grams. And then you're going to convert grams to moles. And then by writing a preliminary formula, this is the divide by small step. So remember, we have percent to mass and then mass to moles. And then divide by small to do this, right, here. And if necessary, then you're going to multiply to turn them all into integers. So at the first year level, you were looking for the closest whole number, the closest half, the closest 1/3 or 2/3. At the AP level, you might be looking for the closest 1/4 or 3/4, or you may be even looking for 1/5, 2/5, etc. Okay, I've seen a few in textbooks that go out to sevenths, but nobody recognizes the decimal of sevenths. But definitely keep in mind, like there's some things here that you should keep in mind, that 1/5 is 0.2, 2/5 is 0.4, 1/4 is 0.25, 1/3 is 0.33, and you definitely need to make sure that you are keeping your significant figures to at least as many as you were given, because if you round too soon, then you may end up with a wrong decimal there. So just quick reminder, percent to mass. If you're given percents, then just change it to grams. Mass to moles, use the mass off the periodic table to convert the elements to moles. Divide by small to give you hopefully whole numbers. If you get a fraction, then multiply everybody by whatever that integer is, by the denominator basically. Okay, and then to find the molecular formula, you need the empirical formula. So all of this is just to get the empirical formula. Once you have the empirical formula, then you can divide the compound mass, which is given, by the empirical formula mass, which you'd have to calculate from your empirical formula to find the multiple, and then multiply the formula. So we're going to do a couple of examples. I'm going to do one that's just like what you've always done in the past, and then we're going to use it in a new way, and then we're going to talk about combustion analysis. So this might actually be a longer video than you would hope for, but it's going to have a lot of new information. So this should be a review for you. If you think that you remember how to do empirical and molecular formulas from first year chem, my thoughts would be this would be a great place to copy the question into your learning targets and then try it yourself. And then I will explain it now. So let's see what we can do here. Stop the video if you want, and let's see what we can do. Okay. So I'm going to do percent to mass, mass to moles, divide by small, multiply to whole. And then they asked me for the molecular formula. So I knew this, right? The molecular means that I need the empirical formula first. And then they gave me the molecular mass here. So I can take that last step. So let's go ahead and see what we've got. We have 95.21%, which I'm going to call grams, carbon, percent by mass, and I'm going to call 4.79% by mass, or call that grams of hydrogen. So there's my percent to mass step. I'm going to convert to moles. So this is going to be 12.01 grams of carbon in 1 mole of carbon, and I think I used 1.01 grams of hydrogen in 1 mole of hydrogen. And I found this to be 7.9275. Notice I'm keeping lots of significant figures. 4.7425. I really need to make sure that I don't cut these off short. So I'm keeping lots. So percent to mass, mass to moles, divide by small. In this case, that would be this one, 4.7425. 4.7425 gives me 1 mole of H. And when I divide this out, I get 1.67 moles of carbon. I need to recognize that this is 1 2/3. So this is way too far away to round to anything, to half or to a whole. So I'm going to take this times 3, which means I have to take this times 3, and that gives me 5 carbon and 3 hydrogen. And so this sets up my empirical formula as C5H3. Okay, this is the empirical formula. So if I want the molecular formula, I need to figure out what the mass is. So the mass of this from the periodic table is 5 times 12. I can pretty much use whole numbers at this point, and 3 times 1 because it's going to be really close. So this comes out to 5 times 12 is 60 plus 3. 63 grams per mole is the empirical formula mass. And then I need to decide how many times I need to multiply that to make 252.3. So I'm a multiplier. I do 63 times what gives me 252. And when I do that, I punch it in my calculator and find that that's a 4. Or you can be a divider and you can say 252 divided by 63 equals 4. And that's to find the multiple, right? So the multiple that we're going to take our empirical formula and multiply by will be 4. So this is going to be C5H3 times 4 equals C20H12. And that's the molecular formula. Please note that College Board expects to see all this work. They expect to see the mass of the empirical formula determined. They expect to see you finding the multiple in some way that's written for them. And they expect to see you multiplying your empirical formula by the multiple to get the molecular formulas. So all of the work that's on this page, including finding the empirical formula mass, including finding the multiple, including multiplying the multiple to get the answer, needs to be there, or you may not earn credit for work that you already know. Okay, so that should be review for you. Now I want to kind of use the formula math in a new way. So what I want to do is show you how we can use the relationship of subscripts in a compound to figure out the mass of one element in a compound, etc. And we're going to do this in a way that's asking you for something you've probably not been asked to solve for before. So they want to know, we have an unknown metal, and 3.12 grams of it react with 2.88 grams of sulfur to form this compound. And they want to know the name of M. So this means we need to identify it, and we're going to identify it by finding the molar mass. So we're going to look for the molar mass of that periodic table then, or molar mass of that element on the periodic table to figure out who it is. So molar mass, remember when we solve problems, we always start from the end. What do I need to know? So molar mass equals grams per mole, and it would have to be grams of M and moles of M. Okay, so I need to find the quantities of grams and moles that match each other. And I don't know who M is, so I can't use the mass off the periodic table to do that. That's what I'm looking for. Okay, so I'm going to read my question and see what I know already so that we can kind of see where we're at. I can see that 3.12 grams of M is in the question, so that's going to end up going there. But what I don't know is how many moles of M that is. Okay, so I'm going to need to do all of my work to solve for moles of M so that I can solve for the molar mass. So the way that I look at this is I'm going to set up way down here at the bottom, grams per mole equals 3.12 grams of M, and I'm solving for moles of M to get the molar mass. Okay. So let's see what we know. We know that 2.88 grams of sulfur reacted with that 3.12 grams of M. So, and then we know the formula subscripts, which are moles. So I can use grams of sulfur and convert from grams of sulfur to moles of sulfur. And then I can go from moles of sulfur to moles of M using the formula that they gave me. Okay, so this grams to moles is from the periodic table. 1 mole is 32.07 grams. And then from the formula, for every 2 moles of M, I have 3 moles of S. And now, when I'm all done, I'm going to get the moles of M that went with the sulfur, and that's equal to the 3.12 grams. So I need the grams and the moles that match each other, and that's what I'm going to know. So when I do this math, I got 0.059869. I'm not going to round to sig figs here. I'm just going to carry that number down here, 0.059, this is moles of M, remember, 869 moles of M, and when I do that math, I get 52.11 grams per mole of M. So now I can look at the periodic table. Let's go find one. And I'm looking for the metal that has a molar mass of 52.1. So I see vanadium at 51. I see chromium at just about 52. I see manganese at 55 almost. So I think chromium is my my answer here. Okay, so whoops, sorry. So let's see what we got. All right, let's go back. And we can see that this is chromium. So the name of M would be chromium. chromium. And the compound would be Cr2s3, which is going to be chromium. Oops, let's review your naming. Chromium sulfide, but chromium needs a Roman numeral. And so sulfur would be 2 minus. That's a total of -6. And this has to be +6 divided by 2, so +3 for each one. So chromium 3 sulfide. So this is a new way to use formula math, using the formula and the subscripts in the formula as a way to convert between moles of each substance in there. These tricks, these problem-solving things are going to be helpful for you as you keep going. Okay, let's look at combustion analysis. All right, this is a new way, and I've got 2 examples here. So we're going to do one together on here. I'll give you the answer to the second one, and then if you need more help with it, you can go watch the help video. So combustion analysis is basically figuring out the amount of the elements, the grams of each element in your compound without being given percent and without being given the grams. So basically you're thinking that we're going to use the law of conservation of mass and the math of formulas to find the mass of each of the elements in the compound. So what I want you to see is that if we burn a hydrocarbon and in oxygen, we're going to get the hydrocarbon, it gives you carbon dioxide and water, right? The problem is that if you don't know the formula, this is just CXHY, we have no idea what these amounts are. Okay, so what happens is that the reason that I have this picture that I really like is that you're going to see that all of the carbon ends up in the carbon dioxide and all of the hydrogen ends up in the water. And basically this oxygen, which would probably be an excess reactant, combines with the hydrogen, combines with the carbon to give you those 2 compounds. So if we use the mass of the carbon dioxide produced, we can find the mass of the carbon in the compound. And if we use the mass of the water produced, we can find the mass of the hydrogen in the compound, because every single bit of them went there. There's nothing else over here that has carbon or hydrogen in it. Okay, so nothing else was produced. The carbon and the hydrogen all went into the carbon dioxide or went into the water. If there happens to be a third element present, then you're going to take the initial mass of the compound that you were given and subtract the other elements, the carbon and the hydrogen, from it to find the mass of the third element. So let's do an example together. And I just want you to kind of always be thinking, I have some CH compound. This one also has Cl, so I don't know the subscripts, and I'm going to combust it. And I'm going to get CO2 and H2O and some other something that contains Cl. Okay, but they didn't tell me about this, so I need to just focus on the other 2. All right, so I know that I started with 0.250 grams of the compound, and I formed 0.451 grams of CO2, sorry, this is H2O, and 0.0617 grams of water. And I want the molecular formula. They gave me the molecular mass, so if I want the molecular formula, I need the empirical formula first. All right, so let's talk about how you're going to do this. We're going to start with the carbon dioxide that was formed and find out how much carbon is in there, because that will tell us the carbon that was in our initial compound. So 0.451 grams of CO2. Remember that we can use the masses from the periodic table, and I'm looking for grams of CO2 to grams of carbon. From the periodic table, carbon in CO2 would be 1 times 12, so that's 12.01. And then the carbon dioxide would be 1 times 12.01 and 2 times 16, which is added together to 44.01. And that will tell me then that I have 0.12307, I'm not cutting it off short, grams of carbon. I also found I had 0.0617 grams of water produced. I can do the same thing to find the grams of hydrogen. All of the hydrogen in the compound ended up in the water. So grams of water to grams of H. Be really careful. This is a place where you're going to make a mistake perhaps and try to find grams of H2. But this needs to be grams of H. Remember that it's inside a compound. It is not diatomic at this point. Okay, so this would be from the periodic table 18.02 grams, and to find that 18.02, I did 2 times 1.01. So if you need to remind yourself that it's like that here, you can, but I would say definitely just keep that in mind. Okay, so this is going to give me 0.00691 grams of H. I need to be able to find the mass of chlorine. Remember to find an empirical formula, I'm going to do percent to mass, which I don't have, so I need to find masses, then mass to moles, and then divide by small, and then if I need to, I'll multiply to whole. Okay, so I need the grams of chlorine before I can keep going. So I know that I started with, to find the grams of chlorine, I know that I started with 0.250 grams of the compound. And I can subtract the 0.12307 grams of carbon and the 0.00691 grams of hydrogen and find that this is 0.120 grams of chlorine. And I'm going to go ahead and round to 3 decimals because that's where my compound was. Okay. Now I'm ready to do what I would always do in an empirical formula question. I have masses of all the elements, so I'm going to do grams of carbon to 1 mole of carbon. Whoops. I'm going to do grams of hydrogen to 1 mole of hydrogen. I'm going to do grams of chlorine to 1 mole of chlorine. These all come from the periodic table. 12.01, 1.01, 35.45. And I discover that I have 0.010247, don't cut them off, moles of carbon. I have 0.006841 moles of hydrogen, and I have 0.003385 moles of chlorine. So now I did my mass to moles. I'm gonna divide by small, that would be the chlorine, 0.003385, 0.003385, 0.003385. This equals 1. And what I get from the other two is this equals 3 and this equals 2. And they came out very, very close. Okay, so I need to add a page here. I'm out of space. So what I find as my initial formula and my empirical formula would be C3, H2. Oh, that was weird. H2Cl. This is the empirical formula. And I don't need to multiply to whole because they came out to whole numbers. So I need to find the empirical formula mass. And that would be 3 times 12.01 plus 2 times 1.01 for the hydrogen plus 35.45 for the chlorine. And that equals 73.55 is the empirical formula mass. And I needed to match 146.99, which is what I was given as the molecular formula mass. So times what equals 146.99, or you can do 146.99 divided by 73.55 equals 2. So I'm going to do C3H2Cl times 2 gives me C6H4Cl2 as the molecular formula. Okay, so really the only thing that's new is this idea of finding the masses of the elements from the combustion analysis. This is the new thing. Everything else is review. So think really carefully about that. Think about how you had to find the third element. And I'm going to ask you to stop this and try it on your own. All right, so stop the video, copy it in first. I always do that in the wrong order. Copy the question, stop the video, do your work, check your answer. I'm going to come back on and I'm only going to give you the answer in a minute, not all of the work. So do a really good job of it. Okay, so after I did my work for this, I discovered that the molecular formula is C20 H28O2. Okay, this is the molecular formula of this steroid that was analyzed by combustion analysis. Okay, if you were correct, congratulations, because that means that you just did really well with your first real AP thing. Okay, if you were incorrect, then you can see the work for this on the optional help video that's called Using Elemental or Combustion Analysis. So, and I'll give you an opportunity to practice some more in there. So if you were correct, then that's optional completely. If you were incorrect, then it's highly recommended. All right, there's only one more thing that I want to talk about with you on this, and this would be the difference between an isomer and a molecular versus an empirical formula. Okay, an isomer has the same molecular formula as two isomers have the same molecular formula as each other. So you can't tell from analysis data, from percent composition, from molecular formula, you cannot tell which one you have based on just being given the formula. So in this case, like this formula given to you here is C2H6O. But there are two isomers. Notice that the structure is different. The structural formula is different. In ethanol, the O is at the end with an H, right? So this would be what we call an alcohol group. And you don't know organic chemistry yet, but this is what we call the alcohol group. And in dimethyl ether, in ethers, we have a carbon chain with an oxygen in the middle. Okay, because of this, they have different intermolecular forces. We'll talk about that a lot this year. And the ethanol actually has a really much stronger attraction because it can hydrogen bond. And so I think that this is the boiling point. I didn't copy that part of the chart. Notice that dimethyl ether is a gas at room temperature, and its densities are very different, and its boiling point is much lower. This is way below our freezing point of water, so this is way below room temperature. So this is why dimethyl ether would be a gas. They will probably have different properties due to their intermolecular forces, but notice that they both have the exact same molecular formula. They just have different structural formulas. So these are what we call constitutional or structural isomers. Okay, this was a lot to take in, so definitely practice what you need to practice. If you need to redo a combustion analysis or you need help on that, please watch the optional video. Otherwise, you'll get the opportunity to practice in your practice problems.